Assalamu alaikum. So inshallah today I'm going to revise chapter 7, which is related to the application of second law of thermodynamics in terms of calculating entropy and entropy generation through the system. Entropy is a property of the system measured in kilojoule per Kelvin. The rate of entropy is calculated in kilowatt per Kelvin. And entropy, actually, if you ask it anybody, will just tell you entropy is a measure of randomness of molecules within the system. That's correct, but actually entropy gives us indication about the energy, kilojoule, lost within the system due to temperature rise of 1 Kelvin. This energy is lost in the random motion and the molecular activities of the molecules. And as the temperature increase of the system, actually the molecular activities will be increasing and the losses within the system will be increasing. Also, we do have another term which is called the entropy generation, which is actually the amount of entropy that is generated within the system due to the losses within the system. So any energy loss within the system, let's say heat losses, the friction losses will be converted to heat, the gases will be heat, but actually this heat we cannot convert to work. Just the heat generated due to the friction losses within the system will be absorbed by the molecule, will be used in the molecular activities of the molecule. So we cannot actually benefit from this heat transfer. That's why the entropy that is generated within the system gives us indication about the losses within the system. As the amount of entropy generated within the system increase, this actually means the system does contain actually higher amount of losses. By the way, based on the Clausius inequality, we can prove actually in relation to the second law of thermodynamics that integration over the cycle, integration of delta Q, which is the heat transfer delta Q over T, should be less than or equal to 0. This term actually can be reduced to integration of delta Q over T can be equal to 0 in case when we do have reversible cycle. Reversible mean actually don't have any kind of losses within the system. So if we do have reversible system working on a reversible cycle, so integration of delta Q over T will equal to 0. And this term actually will be for a real cycle or actual cycle, integration of delta Q over T should be less than 0 in case when we do have actual or real cycle. Okay. So for a reversible cycle, we can just indicate this actually subscript reversible, mean actually the cycle is reversible. So integration of delta Q over T should equal to 0. We can actually prove this Clausius statement based on the relation, the second law analysis. And you can see this in the slide. In the first comment, you can see the slide and you can look at actually the proof of this concept, which is called the Clausius inequality. But as you know, actually for any property, so a cycle or something, we do have the integration of any property, let's say delta V of the cycle should equal to 0. Because integration over a cycle mean we are doing starting from one point, doing series of processes and getting back to the same point. So same point mean we do have the same volume. So integration of delta V will be V2 from the initial state up to the final state will be V2 minus V1. If we are working on a cycle, the final state 2 is the same as the initial state 1, so this means delta V is 0. And this is actually applied for any property. Integration of a cycle for any property should equal to 0. But let's look here, we do have integration over a cycle, something here, delta Q over T is equal to 0. So this means delta Q over T represent a property for a system. And based on this, Clausius himself have defined actually this property to be the entropy. And based on that, we have defined the entropy delta S is equal to actually delta Q over T by the condition actually that this cycle, that this process is actually a reversible process. So the change of entropy is equal to only delta Q, that added heat transfer for a temperature rise, let's say delta T, or a temperature T at a temperature T by the condition that the process is reversible. But if the process is not reversible, if we do have a system undergo a process, let's say from state 1, initial state up to state 2. If it is reversible, then delta S will equal to delta Q over T. But if it is not reversible, actual process means we do have losses within the system. Losses within the system mean we should have some entropy is generated. And based on actually the concept of entropy increase, this is the concept of entropy increase, and also you can actually prove this from the slide. We do have delta S should be actually greater than or equal to delta Q over T. And this is actually greater than or equal to delta Q over 2. Delta S should equal to delta Q over T if the process is reversible, and it should be actually greater than delta Q over T for the actual process. So if we do have a system undergo actual process from 1 to 2, we can calculate delta S. It should equal to integration delta S, the total value after integration, will equal to integration of delta Q over T for any process from 1 to 2 plus the part of the entropy that is generated due to the losses within the system. So this is actually the equation for delta S in case if we do have reversible process, and in case when we do have actual process, we should have delta S is greater than delta Q over T. It can equal to delta Q over T if the process is reversible. But for actual process, it should be greater than this value because of the entropy generated S generation within the system. Okay, and this is actually is applied for the actual process. Type, this is just an introduction, and what is needed actually is to calculate delta S. So if you do have any substance and we need undergo a process from, let's say, initial state, state 1, up to a final state, state 2, and we need to calculate the value of delta S. So in this case, so our target here is we do have a gas undergo, let's say, a process from initial state, state 1, up to a final state, state 2, and our target is to calculate delta S, which is S2 minus S1. How we can calculate it? So first of all, if we do have pure substance with a table, like actually if we do have, in our case, if we do have a steam or refrigerant 134A, so in this case, if we do have a system undergo process from initial state to a final state, so in this case we can say delta S will be just S2 minus S1, which is the total entropy. This is the total value measured in kilojoule per Kelvin. But usually in those tables we find the specific value. So in this case we have to multiply by mass multiplied by specific entropy S2 minus S1. Those specific values are measured in kilojoule per kilogram Kelvin, and this is the mass per kilogram, so the total value will be in kilojoule per Kelvin. So if you do have the working fluid in a problem is a steam or refrigerant, so we do have the table. So in this case at condition 1, at point 1, let's say at point 1, let's say given B1, T1. So in this case we can just go to the table, then we can get S1, and also at the condition at point 2, the condition should be given. Let's say we do have B2 and T2. It could be actually any other property, maybe pressure and the specific volume, temperature and the specific volume, any other two properties. Let's say we do have pressure and temperature, then we'll be going to the table, and then we can get the value S2. Just we need to calculate delta S, so delta S will equal to S2 minus S1. Type, let's say we do have any other substance, let's say we do have ideal gas. In case of ideal gas, we do have some relation that should be used. In case of ideal gas or any other substance actually. So in this case, we do have what is called Tds relation. Tds relations can be used in this case. We do have two Tds relation, which can be proved also. I'm not here actually to prove this equation. So the first equation is Tds is equal to delta U plus PdV, and the second equation is Tds equal to delta H minus VdV. And this is the second equation. And this is the first one. Type, based on this, actually we can actually calculate. We can have two equations to calculate delta S. The first equation is delta S is equal to delta U over T plus VdV over T. The second relation is delta S delta H over T minus VdV over T. And those actually the two relations that are called actually the Tds relation. And in order actually to calculate ds, so we have to do actually the integration. So we have to integrate here in order to calculate the total exchange of entropy, which is delta S, which is S2 minus S1. Delta S is equal to integration of delta S, which is integration of delta U divided by T plus VdV divided by T. But in case if we do have an ideal gas, as we said, in case if we do have an ideal gas. Let's start first of all with a case that is actually a little bit simple. So in case if we do have incompressible substance. So let's call it the most ideal gas. So any other case, this two equation Tds relation can be applied for any case actually. Let's consider special cases. So the first case when we do have incompressible substance. Incompressible, which are liquid or solid. So let's say liquid or solid, or in some cases gases, under certain conditions, but the most probably it's liquid or solid. So in this case we do have delta V. This means actually is a specific volume V, which is 1 over density is constant. So this means delta V, the change of volume, delta V is 0. We do have the equation, we do have delta U from Tds relation, delta S is equal to delta U over T plus VdV over T. In this case we do have volume is constant, so delta V is 0, so this term is 0. So this means to calculate delta S will equal to just delta U over T. And to calculate the total value, we have to integrate delta S, total value of delta S, which is S2 minus S1 final entropy minus the initial entropy, equal to integration of delta S, which is integration of delta U over T. In case of incompressible substance, delta U is equal to integration of C average multiplied by delta T over T from T1 up to T2. So this integration will equal to C average multiplied by ln T2 over T1. And this T average, if you remember for liquid or solid, is calculated as the average temperature T1 plus T2 over 2 and using table A3. So the value of C average can be calculated from table A3. So you have to look at actually any application or any problem to be solved. Look if actually the working fluid is incompressible substance, solid or liquid. So in this case we have to apply the equation delta S equal to C average ln T2 over T1. And C average can be calculated at average temperature from table A3. This is the first special case. The second special case when we do have an ideal gas. And actually any gas we can treat it as ideal gas under actually low pressure and high temperature. So usually in your exam or any problem, if he does not mention you actually that this is a real gas and we have to use the compressibility chart, so I will consider it as an ideal gas. When the working fluid is an ideal gas, we do have some relation for ideal gas. We do have delta U is equal to CV dt, and we do have delta H is equal to CB dt. And also we do have the ideal gas equation, which is BV equal to RT, B multiplied by specific volume equal to RT. If we took actually those three equations and we substitute it in the Tds relation and do the integration, and here I will be writing the final equation, then in this case we can get delta S, which is S2 minus S1, will equal to integration of delta U over T from T1 up to T2 plus integration of dV over T also from T1 up to T2. If we did this integration, substitute BV equal to RT and do this integration, so this will equal to, it will be plus R multiplied by ln V2 over V1 directly, and we do have also the second Tds relation, so this will equal to integration from T1 to T2 delta H divided by T minus R multiplied by ln V2 over V1. And those are actually the two relations that I have to use in order to calculate actually delta S when we do have an ideal gas. If you look here, we do have delta U here, still we do have this integration, we do have delta U and delta H. And to calculate delta U and delta H, we do have two cases, the constant specific heat analysis and the variable specific heat analysis. And this should be given for you. You will be asked either to use constant specific heat analysis or variable specific heat analysis. So for the second case, which is ideal gas, let's consider a special case A, considering constant specific heat analysis, which is called the approximate analysis. So in this case, you have to look at actually the given problem. It will just tell you directly either to use the constant specific heat analysis or the variable specific heat. Constant specific heat means delta U will equal to C average delta T. C average you can take outside. So in this case, to calculate delta S using the constant specific heat analysis, it should equal to CV average multiplied by ln T2 over T1 plus R ln V2 over V1. The second integration delta H will equal to CV average. Integration of delta T will be over T will be ln T2 over T1, okay, minus R ln B2 over B1. So using the constant specific heat analysis, if he asked you to use constant specific heat analysis and we need to calculate delta S, so I will be using either those of two equations, and CV average and CV average are calculated at average temperature, and this is calculated from table, as you know, table A to B. You can calculate CV average or CV average, any of the two equations, okay, can be calculated, and then we can use any of those two equations. If pressure V2 and V1 are given, I can use this equation. If V2 and V1 are given, so I can use the first equation. But the whole way T1 and T2 should be zero in order to calculate delta S. Type, this is called the constant specific heat analysis. The second special case, when we do have an ideal gas, this is still ideal gas. Ideal gas. When we do consider the variable specific heat analysis. Variable specific heat analysis, which is called the exact analysis. This means in this case delta U will equal to integration of CV dt, and we have to do actually this integration. CV is function of temperature, and in this case we have to integrate CV of T, which is function of temperature dt over T, and we have to do integration in this case, and also like this for the CV. But in this case actually they have done actually the first integration, and they came up actually with the relation delta S will equal to S naught 2 minus S naught 1 minus R ln B2 over B1. So they consider the second TDS relation, and they did the integration, which is actually this term refers to the integration of CB as function of temperature dt over T from T1 up to T2. So this term is they already have done this integration, and they reduced it to this value S naught 2 minus S naught 1, and those can be calculated from table A17 up to table A25. So you have to look at actually the working fluid. Let's say if it is air is table A17, so in this case at temperature T1, we can just go to the table with the temperature T1, we can get S01, with temperature T2, we can get S02. If it is another substance, let's say oxygen or something, you can select another table, and also at T1 you can get S01, and at T2 we can get S02 or S02. But please don't say delta S is equal to the difference between the two values. We do have another term, this term. Please don't forget. So to calculate delta S for an ideal gas using the variable specific heat analysis, in this case delta S will be calculated using this relation. R is the gas constant, which is equal to the universal gas constant R bar divided by the molecular weight. Universal gas constant is 8.314 kilojoule per kilomole Kelvin, and the molecular weight can be calculated from table A1 depending on the substance. Also the value of R itself directly can be calculated from table A1. Okay. Then we can calculate the value of this delta S. But actually if you look at S01 minus S02, the unit here should be in kilojoule per kilogram Kelvin. S01 and S02. But actually this is only represented in this unit in table A17. In table from A18 I think they give this value per unit mole, not per unit kilogram. So in this case, if you use from table A18 up to A25, you will be calculating delta S per kilomole. This is kilojoule per kilomole Kelvin. It will be S02 bar minus S01 bar minus R bar MB2 over B1. What I mean actually, starting from table A18 up to table A25, this value S02 minus S01 will be given in the table per kilomole, not per kilogram. So in this case I have to use this equation. So it will be delta S per kilomole, S02 minus S01 minus R bar in this case, not R. This is the universal gas constant, which is 8.314 multiplied by MB2 over B1. And in this case, but what I need actually finally is delta S per kilogram. So in this case, we do have delta S per kilomole equal to delta S per kilogram multiplied by the molecular weight, or we can say delta S per kilogram equal to delta S per mole divided by molecular weight. And the molecular weight, as we said, can be just calculated from table A1. So you will be calculating delta S using this equation for table from A18 I think, and then you can just get this value per kilogram equal to delta S per kilomole divided by the molecular weight. And this is actually the second special case. This is 2A ideal gas, 2B ideal gas. Type the third special case will be also for ideal gas, but ideal gas undergo an isentropic process. Isentropic process means we do have a reversible adiabatic process, and in this case isentropic means the entropy is constant. We don't have losses, so the entropy will be fixed. We don't have losses. So in this case we do have delta S will equal to 0. So case 3, when we do have ideal gas, and we will need actually this equation later on when we need to calculate the entropy generation for a system. This is very important. When we do have an ideal gas undergo an isentropic process. So just we do have an ideal gas from state 1 up to state 2, but the process is isentropic. Isentropic mean actually the change of entropy is equal to 0, or S2 is the same as S1. Also in this case we do have two cases. When we are following approximate analysis, which is called the constant specific heat analysis. This is constant specific heat. Okay. Constant specific heat analysis. So if you get back to the equations that we have written to approximate analysis to calculate delta S, just equate this equation to 0, then we can get actually 3 equations. Those 3 equations can be applied directly when we do have an ideal gas undergo an isentropic process. Those 3 equations are T2 over T1 is equal to V1 over V2 to the power K minus 1 over K. K is the specific heat ratio, which is CV over CV. Can be calculated also from the table. We can get also another relation, which is B2 over B1 is the same as V1 over V2 to the power K, and we do have T2 over T1 is the same as B2 over B1 to the power K minus 1. Let me just check those equations. T2 over T1 equal to V1 over V2 to the power K minus 1, and we do have T2 over T1 is the same as B2 over B1 to the power K minus 1 over K, and we do have B2 over B1 V1 to the power V1 over V2 to the power K. Okay, so that's correct. So those are actually in this case the 3 relations. I don't remember Yani, but you have to remember for your exam. So for approximate analysis, T2 over T1 is V1 over V2 to the power K minus 1 over K to the power K minus 1. B2 over B1 is V1 over V2 to the power K. T2 over T1 is B2 over B1 to the power K minus 1 over K. So in this case, if you do have B2, B1, T1, then you can calculate T2 using this relation, and so on. If you do have T2, T1, V1, we can calculate actually V2 also using this relation. So if we said we do have an ideal gas undergo an isentropic process, so in this case, if he asked you to calculate using the approximate analysis, we can apply actually those three equations. Type there is another case if he actually if you are required to consider the exact analysis or variable specific heat analysis. So case 3b for exact analysis or variable specific heat analysis. Variable specific heat analysis. So in this case, we do have this relation delta S, which we said is the node 2 minus S node 1 minus R lim B2 over V1. When we do have an isentropic process, this term should equal to 0. I will just go through 2-3 steps through this to understand. So in this case, as this is equal to 0, so we can say B2 over B1. You can just reduce it. It will equal to exponential of S02 raised to node 2 divided by R divided by exponential of S node 1 divided by R. We can just call actually this term as B relative 2 divided by B relative 1. I will call this just as B relative and this one as B relative. This is B relative 2 and this is B relative 1. So we can get this relation B2 over B1 is B relative 2 over B relative 1. And we do have, if we do have a gas undergo a process from 1 to 2, we can say B1 V1 over T1, V2 V2 over T2. And based on this relation also, we can prove that V2 over V1 is the same as actually V reduced V relative 2 over V relative 1. And this is actually the second equation following the exact analysis. But what will be given for you? It will given for you here, let's say V1 T1 a gas, and we do have here, let's say we do have here B2, and we need to calculate the final temperature T2. We do have a gas undergo an isentropic process. Following the exact analysis, in this case I will just be taking T1, just go to table from A17 to A25. So first of all, B reduced, so B relative and V relative are just calculated from table A17 up to A table A25, depending on the given gas. You will find in this table at a given temperature, let's say table A17, at a given temperature here, you can just find in the table, you will find here S0, S0, and also you will find here, you will find the internal energy, you will find the enthalpy, and here you will find the B relative, and here you will find also V relative. Okay, so at a given temperature T, we can just go to the table. If T1 is given, so go to table A17 up to A25, one of them, if it is air, it will be A17. Then in this case, you can get B relative 1. And then I need to calculate T2, so I can calculate B relative 2. So B relative 2 over B relative 1 is the same as B2 over B1. We do have B2 and B1, and we got already B relative 1 from the table. Then we can get actually from this relation B relative 2. B relative 2 go to table from A17 up to table A25, one of those tables. Then we can get the temperature T. Okay, so in this case, this is actually much easier. So just I will be using those relation B2 over B1 is B relative 2 over B relative 1. V2 over V1 is B relative 2 over V relative 1. If it is given, we do have an ideal gas undergo an isentropic process following the variable specific heat analysis. So at temperature T1, just to go to the table, get B relative 1, and then we can calculate B relative 2. Go to the table, same table, we can get the temperature T2. But let's say V2 and V1 are given. So in this case at T1 I can get V relative 1. And then we do have V2 and V1, we can calculate V relative 2. Go with the V relative 2 to the same table, we can get the temperature T2. And this is actually the third special case. So we have learned how to calculate delta S. If we do have steam or refrigerant, I will be using table. This is very direct. Is delta S will equal to S2 minus S1. S2 and S1 can be just calculated from the table at the given condition. The second special case, when we do have incompressible substance, we have proved this relation for delta S. And when we do have an ideal gas, when he said we do have gas, you have to keep in mind which method you will follow, either constant specific heat analysis or variable specific heat analysis. And we have proved actually the relation for this case. Constant specific heat, I can consider average specific heat. Variable specific heat, I will do the integration, but actually I will be using the table because they already have done this integration. The third special case is ideal gas undergo an isentropic process, and also we have to follow either the approximate analysis or the exact analysis. This delta S will be used actually to calculate the entropy generation within the system. So inshallah, next class inshallah, as a continue for this revision, to complete this revision, I will be calculating entropy generation. To calculate entropy generation, we have to be able to calculate delta S. It will be a function of delta S. So we have to know actually those procedure. So we'll continue inshallah in the next class.